right, we're about to begin a small miniature unit on probability. We'll call this chapter 13. So 13.1 is about experimental and theoretical probability. So before we begin, I want you to do the 5-minute check on your own and see how well you do on those. So go ahead and pause the video right here and do number 1, A, B, and C. All right, let's see how you did on this. So it says you select a letter at random from the words, some are fun. Express each probability as a fraction, a decimal, and a percent. So the probability of picking a vowel, there are 3 vowels over 9 total letters. So a fraction would be 3/9 or 1/3. The decimal would be 0.33. And the percent would be 33%. The consonant would be the other 6 letters. So 6 out of 9, that would be your decimal, which you could reduce to 2/3. That would be your fraction. Your decimal then would be 0.67, and your percentage would be 67%. And then the probability of an M or a U, so 1, 2, 3, 4 out of 9 is either an M or a U. We can't reduce that. As a decimal, that would be 0.44, which would be 44%. So this is what we call theoretical probability. So this is the probability that you are used to. So let's go to your Cornell sheet and let's write down theoretical probability. That is the favorable outcome divided by the set of all outcomes. So you can give it as a fraction, a decimal, or a percent. And so a fraction like 1/12 would give you a decimal 0.08, and that would be 8%. So remember moving the decimal 2 places to the right. And you always want to use your rounding rules, 5 or above, give it a shove. Always strictly follow those rounding rules, okay? This is different from what is called experimental probability. So experimental probability is when you actually run an experiment where something actually happens. So you toss a coin 10 times and heads comes up 8 times and tails comes up 2 times, then your experimental probability would be 8 out of 10 would give you heads, okay? So to express experimental probability, that's the number of times the event occurs over total number of trials. Now this is different probably from any probability that you've done. Mostly the probability that you have done is all theoretical probability, okay? Now another new idea possibly is what's called a complement. So a complement is this, let me show you, probability of choosing a vowel is the complement to the probability of choosing a consonant, because every letter here is either a vowel or a consonant. And so when two events are complements, that means their probabilities are going to be the opposites of each other. Meaning that if you take this probability, a probability of choosing a vowel, and you subtract that from 100%, then that would leave you with the probability of choosing a consonant. So you only have 2 options here. It's either a vowel or a consonant, and that makes those complements because together they make up all 100%. So a couple things we want to write down about a complement. First of all, the probabilities of complements add up, add up to 100%. Okay, so we'll write vowel and consonant. Okay, so those are complements. If you only have two color shirts in your closet, black and white, then the probability of choosing a black shirt would be the complement to the probability of choosing a white shirt. That's only if you have only black and white. Okay. The other thing we know about complement is the way they say it. So if it would be the set of outcomes not included in an event. And that sounds a bit confusing, but this is what I mean. So the probability of choosing an odd number, its complement would be the probability of choosing an even number, because numbers are either odd or even. So together they are complements, but the complement to the probability of choosing odd is the probability of choosing the even. Okay, so let's talk about the next one, number 2. The picture shows the jeans in Jason's closet. He selects a pair of pants with his eyes shut. Give each probability as a decimal. So we're giving it as a decimal. I want you and your partner to do number 2, A, B, and C. So pause the video here. All right, let's see how we did. Probability of choosing a khaki. Well, there are 8 pairs of pants in the closet. 3 of them are khaki, so 3 out of 8, and we're giving it as a decimal, it says, so 0.375. If you wrote 0.38, that's okay too. Probability of choosing red pants. Well, there are 0 red pants out of 8, so that would be 0. You don't have to really put a decimal. And then the probability of choosing blue or black. Well, there are 2 pairs of blue and 3 pairs of black, so that's 5 pants that either are blue or black, so that's 5/8, and so we get 0.625. Again, if you wrote 0.63, that is okay, since it's not specific as to how far it wants you to take the decimal. All right, so we did theoretical, complement, and experimental probability. We can talk about a simple event as well. And we can talk about sample space when we get a little further. So let's talk about simple event. Okay. So a simple event is an event with only one outcome. Like rolling a dice and getting a 6. Okay, that would be a simple event. A compound event would be the flip side of that. So an event with multiple possibilities or outcomes. And so an example of that would be rolling a die and getting an even number. Okay, so if there's only one way to get a 6, then that's a simple event. If there's multiple ways to get an even number, so 2, 4, or 6, then that's called a compound event. Okay, that's the difference between those two. I'm not going to stress that very much. You're not going to be asked to identify if it's simple or compound, just something that's important to think about. So let's go back to the examples here. Okay. So you attempt 16 free throws in a basketball game. Your results are shown. What is the experimental probability of making a free throw? So now we're saying that there were actually these throws were actually made. So this is like running an experiment. You shoot the ball 16 times and you keep a tally of what happened during those 16 times. So that makes this experimental probability. Okay. So we know that there are 16 tosses. Okay. And the 0 means you missed the free throw. The 1 means you made the free throw. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 out of 16 times you made the free throw, and so that's 50%. So your experimental probability is 50%. Predict how many shots you will make if you shoot 20 more free throws. Okay. So if you are making a prediction based on your experimental probability, 50% of the time you will make the free throw. So what we do is we take that probability, 50%, and we multiply it by how many more trials you're going to do, 20 trials. So 50% times 20 trials means you'll make 10 more. 10 will be made. That's your prediction. Okay. So making a prediction, we might want to put that on your Cornell sheet. So let's go over here to experimental probability. When you want to make a prediction, that equals the probability times the number of trials. So you just take the probability of the previous experiment and you multiply by how many future trials you're planning on doing, and then that will help you make your prediction. This is actually one of the forgotten things, so we might want to mark that extra special way so we don't forget that. Okay. All right. A bicycle company checks a random sample of bikes. The results are shown below. If the trend continues, predict the number of defective bikes for each batch size. So here's the experiment. They checked 400 bikes and 12 of them were defective. So we know that 12 out of every 400 ended up being defective, which comes out to be 0.03 or 3% defective. That's not too bad. Oh, I'm sorry. There we go. So 12 divided by 400 gives you 0.03, which is 3%. Bump it twice. Okay. Now we want to make a prediction. So we're going to use that percentage or that probability, better to use the decimal, of course, and multiply it by the number of bikes. So here we have another batch of bikes, 1,300 bikes, and we want to know out of those 1,300 how many might be defective. So we take the probability, 0.03, and we multiply that by 1,300. Very simple, okay? And what you'll find is that you'd have about 39 defective. Okay? And you do the same thing for the 3,500. And so you just take the 0.03 and you multiply by 3,500. So you get 105 defective. You might also see a question very similar to this, and it might ask you how many bikes would not be defective. So there's a couple ways you can do it. If we know 105 of them would be defective, we could just take 3,500 and subtract the 105, and that would tell us how many would not be defective. Okay, let's go ahead and go ahead and write that in there so that we have that down in case we see something like that. So that would mean that 3,395 would not be defective. Okay, so you just make sure you read the question carefully and you're answering the one that they want. If these are the defective, then you don't, and they ask you for the ones that are not defective, you just do a subtraction at the end. Okay. All right, the last one in this little section on our Cornell sheet is sample space. And many of you have found sample space before, I think, because sample space is often when we use a tree diagram. So a sample space is the set of all possible outcomes And we often use a tree diagram, or sometimes we use a table to help us identify all the possible outcomes, okay? So if you want to find the total number of possibilities, let's look at this example on the notes. So it says, Mr. Freeze has a choice of waffle cones and sugar cones. On a given day, they have the following soft serve options: vanilla, chocolate, raspberry, and orange. Make a tree diagram to define the sample space. Now, before you define the sample space, we can figure out how many possibilities there are by simply multiplying the number of choices of waffle cones. So that would be of cones, because it's waffle or sugar. And we multiply that by the number of soft serve options, which is 1, 2, 3, 4. And that gives us 8 total possibilities. Okay? And so if you go back to your Cornell sheet, if you want to find the total number of possibilities, you multiply the number of choice A's times the number of choice B's, and that'll give you your total. Now sometimes you have multiple choices, so you may be multiplying 5 different things together if you're going for a drink, a main course, a side, a dessert, and another side that we have to fill in there. So it depends on how many choices you have. You just multiply how many possibilities there are for each choice, multiply them all together. Very simple, okay? So we know we have 8 possibilities, and we're going to build our tree diagram here. So a lot of you have done this before. You can build your tree diagram vertically or horizontally, whichever way you want. But when you first begin, you have a choice between a waffle cone and a sugar cone. So that's your first choice. But if you choose a waffle cone, then you've got 4 options for ice cream, either vanilla, chocolate, raspberry, or orange. And same thing for the sugar cone. You have 4 choices. So vanilla, chocolate, raspberry, or orange. So when we write out the possibilities, we've got waffle vanilla, waffle chocolate, waffle raspberry, waffle orange. Then we've got sugar vanilla, sugar chocolate, sugar cone raspberry, and sugar cone orange. And there are your 8 possibilities. That is your sample space. All 8 are included there, okay? Now, this one says probability, you want to find the probability of a waffle and an orange. So, waffle and orange is right here. And there's only one way you can get a waffle cone and orange soft serve. So that's 1 out of 8 possibilities, which you can write as a decimal if you want, or you can leave it as a fraction as long as it's simplified, okay? So defining the sample space for that is not too challenging. Defining the sample space sometimes can get a bit challenging, especially if you are limited in space. The next one says, define the sample space for tossing 3 coins. So we know that for the first coin, let's talk about how many possibilities we have. For the first coin, we have 2 possibilities, heads or tails. For the second coin, we have 2 possibilities, heads or tails. And for the third coin, we have 2 possibilities, heads or tails. So 2 times 2 times 2 gives us 8 total outcomes or possibilities. Okay, so we wanted to define the sample space for tossing 3 coins. Now, you could start listing them out and hope that you get all the possibilities, but the tree diagram is really going to help you make sure that you have everything. So the first one, you're either going to get a heads or a tails, okay? Now, if the first one flips and it's a heads, then you have 2 options there, heads or tails on the second coin. Same here, heads or tails. Now, let's suppose you flip it and you get a heads. The second time you get a heads, then you have 2 options there, heads or tails on the third one. So we just have to keep building this, heads or tails, heads or tails, heads or tails. Not too bad, okay? But then we need to write out the sample space. So this just tells us 1, 2, 3, 4, 5, 6, 7, 8. We did in fact get all the 8 possibilities, but we have to write out the sample space. So when it says define the sample space, you can't just make a tree diagram. There's another step we have to write it out. So HHH is the first one. This one is HHT, HTH, HTT, THH, THT, TTH, and TTT. Now, it doesn't say that you have to make a tree diagram, but if you were to start listing these out, there's a very good possibility that you would miss one of the possible outcomes. And you'd probably spend more time trying to figure out which one you missed than if you just make a tree diagram. So sometimes even when it doesn't ask for a tree diagram, it's easier to make the tree diagram so that you can more quickly find your sample space and be convinced that that is the entire sample space, okay? Now we're going to find a couple probabilities here. Theoretical probability, of course, because we're not tossing the coins and counting them. We're just using what could actually happen. So the probability of getting 2 heads. So let's assume this means exactly 2 heads. All right, so we have here this possibility, this one, and that's it. So exactly, probability of getting exactly 2 heads is 3 out of 8, or 0.375. Probability of getting 1 head, we'll use the red here. We've got 1 head here, 1 here, and 1 here, which is also 3 out of 8, or 0.375. Okay. C says, if you toss the coin 50 more times, how many times would you expect to get 2 heads? Okay. And even if it said, if you toss the coin 50 times, let's just say 50 times, because we didn't run in any part of an experiment yet, so it's not going to be more times, just 50 times. So how many times would you expect to get 2 heads? Now, since the probability of getting 2 heads was 0.375, we take that probability and we multiply it by the number of trials we're about to do, which is 50. So 0.375 times 50 comes out to be 18.75. So about 19 times. It's a very good idea. Now, I said that you could round this to 0.38, but in statistics and probability, we want to get the closest answer. We want to be as accurate as possible. So it is actually best if you don't chop that off and round it, but you use the entire decimal so that we can be as close to the proper answer as possible. So just keep that in mind when you're working on this probability unit. All right. With your partner, toss 3 coins 20 times. Record the results below. So the sub has some coins for you, and you just need to, as quickly as possible, write down what you got with your partner. So we have one partner toss all 3 coins and then write down what you got. So let's say I toss all 3 coins and I get heads, heads, tails on the first one. I'll write heads, heads, tails. Then toss the coin again and I get tails, tails, tails. And the next time I toss them again, I get a tails and a head and another tail. Okay, so do that as quickly as you can, 20 times. Record your results, and then you're going to find the experimental probability from the results of your 20 tosses. So how many times did you get exactly 2 heads? And how many times did you get exactly 1 head? And after we run that experiment, we're going to compare the experimental probabilities with your, these are your theoretical probabilities with what you got when you ran the experiment, and see how that went. So we're going to pause the video here so we can complete that with your partner. Okay, so let's see what happened. You tossed the 3 coins 20 times, so we know this has got to be 20 down here. And let's suppose that you had 7 out of 20 times was 2 heads, okay? And you are going to divide that to get a decimal. And your answer, of course, would be different. So let's say this is just what I got, 0.35. And then how many times did I get one head? Let's say mine was 12. Okay. So your answers will be different. All right. And they're not different wrong. They're different just because all of the experiments will run differently, of course. Now, when you compare your probabilities to these probabilities, they may be close or they may not be close, like these two. But if we were to add the entire class up, so if everybody wrote on the board or we raise your hand and we add them together. So let's say there were 5 groups in the class. Okay, so if there's 5 groups in the class and they each toss the coin 20 times, that means there'd be 100 total trials. So what you could do is gather that information, and what you'll find is that if you added all of your information together across the class, okay, you will find that this number, so now let's say out of the 100 trials, 37 times there were 2 heads between the entire class, which comes out to be 0.37. What you're going to find is that once you add the whole class together, there'll be a little less variability, and this number is going to get closer and closer and closer to the theoretical probability, which we had up here, which is 0.375. And if, let's say if you did 1,000 trials, there's a very good possibility that if you ran 1,000 trials within the class, that number is going to potentially get right on to that theoretical probability. So the fewer trials that you do, the less chance that you're going to hit right on that theoretical probability. But as you do more and more and more and more trials, that number is going to get closer and closer and closer to the actual theoretical probability. So you can add those together for the 2 heads and see what you get for the class. Also add them together for the 1 head and see if that gets closer to the 0.375 that we got at the top. All right, last thing, defining the sample space for rolling 2 dice. Okay, so we have a chart already for the rolling the 2 dice, and I'm just going to show you how to start it, and then you can complete these probabilities, and we'll check and see how you did. So if you roll the dice, okay, and you get a 1 and a 1, then this is what your sample space would look like. A 1 and a 1. This would be a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6, okay? And then you'll keep going. So here this is 2, 1, 3, 1, 4, 1, 5, 1, 6, 1. So what I want you to do is, as quickly as you can, write out the full sample space for rolling 2 dice, and then I want you to find each of these probabilities, A, B, and C. This is the last thing we're going to do in the lesson, so go ahead and pause the video and see how you do. All right, so the probability of rolling doubles. Now doubles are going to go right here, down this area here. Okay, all of these come out to be 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So 1, 2, 3, 4, 5, 6. 6 out of the 36 trials, you would roll doubles, which is 17%, or 0.17 if you like. Sum is greater than 7. So 6 plus 1, that's not greater than 7, but 6 plus 2 is greater than 7. So this is greater than 7. 5 plus 3 is greater than 7. What you end up with is this this triangle down here. These are all greater than 7, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So 15 out of the 36 will add up to be greater than 7, so that's 42%. And then the probability where the sum is less than or equal to 7. So this is easy. These two, and I'm going to answer this question right here. B and C are complements. But let's go ahead and say, if we add up how many are less than or equal to 7, that would be everything else. Because if these are greater than 7, then these along this diagonal are going to be exactly 7. And then these above that diagonal would be less than 7. So it actually ends up being 21 out of 36, which is 58%. So 15 of them are greater than 7, 21 of them are less than or equal to 7, and you'll notice these two add up to 100%. And so B and C are complements. It either has to be greater than 7 or it has to be less than or equal to 7. So yes, they are complements because the probabilities add up to 100%. Yay! I'm sorry. Here's what I wrote. All right, have fun.